The age of the earth, also known as geologic time, stands as one of the main conflicts that exist today between biblical teachings and those of natural science. But it should come as no surprise, given the anti-catastrophic bias of geologists, that all geologic features formed during the global flood would be misinterpreted. We should expect them to be misinterpreting geologic features today. Their adherence to slow and gradual geologic processes as an explanatory mechanism is the key to understanding why secular science ages the earth so far beyond what the Bible would allow for. Where does the concept of geologic time come from? Well, geologic time is based on an interpretation of the rocks that were called sedimentary rocks. Now, sedimentary rocks, as I mentioned before, are new rocks that have originated from granites and other basement rocks that were weathered away. They were transported to new area and deposited there. They're new rocks. And there are three main types of sedimentary rocks. There are sandstones, made up of sand particles when those are deposited. Shale is made up of tiny particles of silt and clay. And then you have limestone, which is a sedimentary rock hardened by calcium carbonate from the shells of marine invertebrates. Basically the same stuff that we make concrete out of. Well, today in most places, sedimentary rocks can be found that are hundreds of feet in thickness, and in other places there's literally kilometers of thickness of sedimentary rocks. Limestone exists in such vast quantities that it has been used in the construction of roads and buildings. The roads in Jerusalem, for example, are made out of what we call Jerusalem limestone, or the tremendous pyramids like the one you see here at Giza, which are made entirely out of this sedimentary rock. Sedimentary rock typically exists as distinct layers or what we call strata. Now, generally, geologists view the various layers as forming in different depositional environments. For example, when the region was a desert, you had one type of sediment forming there, and then it was a swamp, you have another kind of sediment forming there, and then maybe it was inundated with an ocean, and you have a different kind of sediment forming there, and then it switches back to a desert. Thus, the different layers form during different depositional environments. And thus it is argued that these layers are separated by vast eons of time. Vast eons of time separate these different layers. Well, this sedimentary rock strata contains abundant fossils and is referred to today as the fossil record because it is believed to contain a recording of history. Much like tree rings record the history of a tree's life, or ice cores record the history of that formation of that ice. They argue that these various layers of sedimentary rocks that contain fossils record snapshots of time. That you had different plants and animals living during this time than you had during the time above it, and different plants and animals living in a different time above that. Well, as I look at in other presentations, that's not enough to show evolution. That there's different plants and animals in this layer than the one above it doesn't show that they've evolved. They must be able to trace the evolution of an organism through these various layers for that to really be showing evolution. Well, it is argued that all of the layers of the fossil record can be found on less than 1% of the Earth's surface. You see, all of these layers can be found on less than 1% of the Earth's surface. So where do we get this fossil record from? Now, I want to illustrate this point a little better for you. This is a map from the U.S. Geologic Survey, and this diagram shows the layers of the fossil record, what we call the geological column, that are on the surface in North America. Okay, so look at this map well. You can see it's color-coded on the right side, and then the North American continent, you can see there, is color-coded to show the layers of the fossil record that are on the surface in North America. Now, there's something what you'll notice here. For example, look up in Canada. You can see all that area in Canada that's covered with red. Well, you see where the red is down there on the bottom of the scale on the right. I mean, all of that geological time above those red layers is missing from all of that area of Canada. You see what I'm looking at there? So The fossil record, as it's been painted, is found literally almost nowhere on the planet. In fact, most of the fossil record is missing from most of the places on the planet, like in that area that you see up there in Canada. Look at all the geologic time that's missing from all across Canada. Well, where did they get the fossil record from? Let me show you how they assembled it together. They assembled the fossil record together by looking at exposed layers of rocks in different locations and finding commonalities. Finding the same layer that's present here is also present over here. So, for example, the Kaibab limestone can be found close to the top of the Grand Canyon. So the Grand Canyon by the way, this is another U.S. Geologic Survey diagram showing how these layers are aligned. Okay, but you'll see how the Kaibab limestone can be found close to the top of the Grand Canyon, but is on the bottom of Zion National Park. You can see how I've linked those layers up to you for you. The Navajo sandstone and other formations can be found at both the Zion National Park and Canyonlands National Park, which is to its right. The Morrison Formation, which is rich in dinosaur fossils, can be found in both Canyonlands and Mesa Verde. And then the Curtis Formation and the Strata sandstone can be found on both the Mesa Verde and Bryce Canyon. So by comparing the exposed layers at various locations and finding those layers to be common to both, they assume the layers above and the layers below are just missing, have eroded away, and those kind of things. This is how they've eventually assembled together what they call the fossil record, is by examining layers in different locations. But fossils are frequently found out of place. We should not really assume that this fossil record, as they show us, is actually set in stone, because like I say, many of these fossils are found out of place, often by millions of years. The fossil record, in fact, described by paleontologists, is really better understood as a statement of evolutionary thinking, or the way that the fossil record should be if it was intact. This is kind of how they say it should be. Well, we know that strata, these layers of rocks, do not take millions of years to form. We know this experimentally. We can easily reproduce this in a laboratory. Experimentally, we know that particles don't fall at the same rate. If you take a cylinder like the one, a glass cylinder, and put a bunch of dirt in the thing, bunch of sand, and shake it up, it will automatically form different layers. The larger particles will settle out first. Smaller particles will settle out after. So things like their size, their density, their shape can affect how quickly they will settle out. And so it doesn't take long periods of time for layers of rocks to form. We can point out some geologic features around the world that point to this as well. This canyon near Walla Walla is actually exposed Missoula flood deposit. So remember, the Missoula flood only lasted a couple of days as these waters plowed across eastern Washington. Well, the canyon wall that you see on the left there is a wall of rhythmite deposits that were formed during the Missoula flood. But you can see distinct layers there. Distinct layers don't take long periods of time to form. They even form in catastrophic situations, like during the Missoula flood. In many mountainous areas, we can find rock layers that are thousands of feet thick that have been folded and bent without fracturing. But how can this happen if they were laid down separated by millions of years and have already hardened? These layers are at the Zagros Mountains along the southwest coast of Iran. These are from the Sullivan River in southern British Columbia. Hardened rock layers are brittle. Limestone, remember, is hardened by the mineral calcium carbonate, which is the same stuff we use to make concrete. You can't go folding concrete like that, but if concrete is still wet, it can be easily shaped and molded and before it sets up. The same principles apply to sedimentary rock layers as well. They can be bent and folded soon after the sediments were deposited, before the natural cementation has had a chance to bind the particles together into hard, brittle rock. Well, in 1669, Nicholas Steno, shown here, outlined the principles of stratigraphy, or strata formation, which are now commonly known as the laws of stratigraphy. These include the principle of lateral continuity. It is believed that strata originally extended in all direction until it thinned out at the continental shelf in the ocean, or was terminated by some geographic barrier like a mountain range. The sediments that fossils are found in are laterally continuous or horizontally indefinite. They basically extend forever in all directions, unless they're terminated by some kind of geographic barrier or taper off at the continental shelf. Well, this is not what we see today. We do not find sediments forming in laterally continuous beds blanketing the continent. They are formed in really small, little isolated sedimentary beds, like where a river empties into a bay or into a lake. It will deposit its sediments right there in a fan-shaped the river delta. But this is one of the laws of stratigraphy, is called the law of lateral continuity. We can find this. This law of stratigraphy is due to observations that the layers of sedimentary rock that fossils are found in stretch for hundreds of miles in every direction. Some can be traced for thousands of miles, all the way from one side of the continent to the other side of the continent. This law and these observations stand as overwhelming proof of the biblical flood to all those blinded by their worldview, because only such an event is capable of laying down such broad-reaching beds of flood sediments. The U.S. Geologic Survey diagram, this one, again, a U.S. Survey Geologic diagram, shows the layers on the right from the Grand Canyon and how those same layers can be traced all the way across Arizona into Utah. It's what's called the law of lateral continuity. But again, we don't find sediments forming like this today. Charles Lyell's thought that the present is key to the past. Well, we don't find sediments forming like that today. We don't find sediments forming in sedimentary beds that are hundreds of feet across. We find these little fan-shaped deposits and these river deltas forming. That's our biggest, most wide, extensive sedimentary bed that we can point to, our river deltas. Nothing like this is forming today. Nothing like this. And yet it is one of the laws of stratigraphy. One of our laws of how strata is found in the fossil record is the law of lateral continuity. Well, Steno's other principles of stratigraphy were these: the principle of superposition, that oldest strata lies on the bottom and younger layers are above. He said this: at the time when any given strata was being formed, all the matter resting upon it was fluid, was water, and therefore at the time when the lower stratum was being formed, none of the upper strata existed. We can all, I think, get behind this, that a layer on the bottom has to be there before a layer on the top can be formed. That's basically all it's saying. And there's also the principle of initial horizontality, that as particles settle by gravity, so strata was originally horizontal. Steno said this: strata, either perpendicular to the horizon or inclined to the horizon, were at one time parallel to the horizon. So he argued that all the sedimentary rock layers were originally horizontal, and they have been bent or folded since they were originally formed. So the law of superimposition and the law of original horizontality were other two laws of stratigraphy, but simple demonstration can show that both of these laws are also not true on any kind of universal basis. These, you can see in this video, these particles of light and dark particles are forming distinct layers at the exact same time in violation of the law of superposition, but the layers are also not forming horizontally either. It's violating the law of initial horizontality. Particles of different densities will separate into layers when simply rolling down hills. Well, numerous physical actions can create strata rapidly. Any natural process that can suspend particles for even a brief period will cause them to form distinct layers. It doesn't take long periods of time. It doesn't take changes in depositional environments for different layers to form. Mud flows, so I skipped past that. Most of these you'll be familiar with. Wind action can cause layers to set up. River action, landslides, and mud flows. Liquefaction and turbidity currents, though, are probably unfamiliar to you, so I'll spend a little time showing what those are. But mud flows are very, very destructive features, geologic events, and can leave massive layers of strata in a single day. And we can point to a number of examples of mud flows that not only form strata, but the erosion capability of mud flows is astounding. We now know that erosion, it is not water that causes most erosion, it's what water is carrying with it. That when coming down at elevation, when coming down at velocity, water is able to pick up significant sized materials with it. Not just sand or gravel, but boulders, as we've seen in the case of the Missoula flood. Trees are swept along, and here is the real power of erosion. When water picks up gravel and rocks and trees and all kinds of stuff and carry that, then you have some real erosion taking place. But there's also liquefaction. Liquefaction occurs when vibrations or water pressure within a mass of soil causes soil particles to lose contact with one another and take on the behavior of a fluid. As a result, it will take on fluidic properties. It loses its ability to support weight and can even flow. This condition, what we call liquefaction, is usually temporary and caused by earthquakes and these kind of things, but likely to have been the kinds of processes taking place during the global flood as well. Turbidity currents was another physical phenomena that's able to create widespread strata. Now, this is an example of a turbidity current that's been created in a laboratory flume, one of the experimental devices that's used to study flood-based processes, fluidic processes. But this is a turbidity current. Basically what it is an underwater landslide. So turbidity currents are these things called underwater landslides, and we can identify turbidites, a specific type of sedimentary rock that is produced by turbidity currents. For example, the two deposits that you see here are both turbidites. So it's a sandstone deposit where where it has a graded bedding. Coarse particles are on the bottom, grading to ever finer particles on the top. So it's one mass of sedimentary rock that was flowing at the same time. So the coarser particles are left on the bottom and gradually gets to finer particles on the top. So we know what these things look like, and we can point to some of them in the fossil record. The sandstone layer identified here at the Grand Canyon is a turbidite deposit. And this deposit ranges in thickness from 125 to 325 feet in thickness. Now that's an underwater landslide that left a deposit ranging from 125 to 325 feet in thickness. Well, geologists today have concluded that the Depeat sandstone was due to a series of underwater flows racing along at speeds of close to 90 miles per hour. Such devastating flows comprise a highly energetic event and must have resulted from an event with even greater causal power. Well, today, geologists estimate that as much as 30% of the sedimentary rocks exposed to the Grand Canyon may in fact be turbidites. 30% of the sedimentary rocks in the Grand Canyon, they argue, may in fact be turbidites, resulting from turbidity currents, underwater landslides. Well, a map of the Depeat sandstone deposit, that one we looked at the Grand Canyon, this is a map showing where those same deposits can be found over North America. Now, this map was accumulated from oil well drilling information, but if that is the result of an underwater landslide, I mean, what else could cause a formation like this other than a continental-wide flood catastrophe? The evidence that this provides for a global-scale flood catastrophe is immeasurable. Well, some geologists suggest that 50% of the world's sedimentary rocks might in fact be turbidites. It is also noteworthy that at the base of the Depeat sandstone is an incredibly flat erosion surface from which the previously deposited material had been eroded away, completely leaving behind a flat surface on which the Depeat sandstone could be deposited. Well, let me revisit the law of superposition quickly and evaluate it against some experimental results. Now, the law again states that the oldest strata lies on the bottom with younger layers lying above it. But this law of stratigraphy has been shown experimentally to not be true in certain types of depositional environments, such as when sediments are flowing. Let me show you an example of this. Now, these are laboratory flumes that are used to simulate erosion in depositional environments and explore the factors that influence these processes, including strata formation. Well, large-scale flume experiments were conducted at the Fort Collins Hydrologics Laboratory at Colorado State University with Professor of Hydraulics and Sedimentology, Pierre Julien. His work was originally published in the Journal of Creation back in 1988. You can find that in the Journal of Creation, Volume 3. Well, in these flumes, watch here, they observed stratified sediments forming in minutes to hours under simulated conditions. Heterogeneous mixtures of particles of different sizes and densities were used to determine how these particles would behave in various depositional environments. They mixed together sand, limestone, and coal, and these were used to demonstrate that both fine lamina and thick layers of beds of sediments could form during these kind of lateral motion experiments. Watch here. You can see two layers forming simultaneously here. Probably one of the most interesting things that they discovered, you can see how you see a dark layer and a light layer forming at the same time. I didn't get to watch much of that. But what they found was that as they altered the rate of flow, so they would have these two layers forming. That dark layer and that lighter layer beneath it would be forming at the exact same time, simultaneously, pretty much. But when they altered the rate of flow, what would happen was another set of layers would start forming on top of that pair, and all of them continued to develop in a prograding manner. And when they changed the rate of flow again, either increased it or decreased it, another set of layers would start forming on the top of those. So you could have multiple pairs of these layers, all that would just continue to form. They would change the rate of flow again. Another one would start to form on the top. They would change the rate of flow again. Another one started forming on the top. I found it very interesting. So what their observation has shown is that when sediments are flowing, the law of superposition does not necessarily hold true. That is, older strata are not always on the bottom and younger strata above them. What would happen is that fine particles would fall between the coarse particles, and the coarse particles rolled across the fine particles, becoming embedded in the layer beneath, causing different layers to form simultaneously, not at different times. More importantly, the time sequence relationship of the strata is much less bottom to top as it is front to back. The newest layers are the ones out front to the flow. The older sediments are the ones in the back of the flow, not bottom to top. And superficially, it is bottom to top. But more significantly, it was front to back, were the ages of those layers. Now, I want you to see something else. Watch here as one of these technicians is removing one of the supports for this bed to show the layers that are inside. Watch here. The researcher cuts through the accumulated sediments to reveal the strata that formed here rapidly. Note both, you can see fine lamina and thick beds of sediments, including a layer of white limestone. The white layer you see there is limestone that is said to only formed in ocean environments. But here it was just limestone and sandstone and coal that were mixed together that formed these layers simultaneously. It didn't take changes in depositional environments to go from an ocean being there to a swamp being there to a desert being there. Those layers formed simultaneously because that's how layers behave.